All right, let's talk about the secret ingredient that turns a kind of clumsy AI model into one that can actually think on its feet out in the real world. It's a concept called regularization, and honestly, it's one of the most important tools we have for building truly smart AI.
So let's kick things off with a super common and super frustrating problem. Picture this. You've spent weeks, maybe months, training this beast of an AI model. It's crushing all your tests, getting perfect scores on your training data. You're feeling good. But then, the moment you show it something brand new, something it's never seen before, it just completely faceplants. Why? What is actually going on here? Well, the culprit has a name, and it's called overfitting. The best way to think about it is like a student cramming for a test. But instead of learning the concepts, they just memorize the exact answers to the practice questions. Of course, they're going to ace the practice test, but give them the final exam where the questions are just a little bit different, and they're totally lost. That's our AI. It's not learning, it's memorizing, noise, errors, and all. So if overfitting is the problem, regularization is our solution. It's this whole collection of techniques that act like a really good teacher. It steps in and tells the model, hey, stop just memorizing. I want you to find the simplest, most general pattern you can. We do this by adding a penalty every time the model gets too complex. This forces it to generalize, which is exactly what we need it to do to perform well on new, unseen data. So here's our game plan for today. We're going to dive deep into the overfitting problem. Then we'll open up our toolbox and look at the weight penalty playbook, a strategy called the network team-up, a tough little data boot camp, and finally, knowing when to blow the final whistle with early stopping. Let's get into it.
First up, let's really get to grips with the overfitting problem and take a closer look at what happens when learning goes completely off the rails.
Okay, so our first set of tools is what I like to call the weight penalty playbook. This is all about keeping the model's internal guts, its weights, in check. So the core idea here is actually pretty simple. A model that has overfit often has these wildly huge internal numbers, or weights. This makes it really jumpy and, frankly, overconfident. It reacts like crazy to the tiniest changes in the input. By penalizing those big weights, we basically encourage a calmer, smoother, more generalized model that just performs better. And this brings us to the two big players in our playbook, L1 and L2 regularization. L1, also called lasso, penalizes the absolute value of the weights. Now, this is a really cool side effect. It can actually force the weights of features that don't matter all the way down to zero, basically doing automatic feature selection for you. On the other hand, you have L2, or ridge, which penalizes the squared value of the weights. This doesn't push things to zero, but it encourages all the weights to be nice and small. This creates a more balanced model, where no single feature can just take over. So think L1 for sparsity, L2 for balance. Next up in our toolbox, the network team-up. This one's all about changing how the network itself behaves during training, forcing the neurons to cooperate better. And the star player here is a technique called dropout. And honestly, the idea is just brilliant in its simplicity. During each step of training, we just randomly turn off a certain percentage of neurons. We just drop them. Why? Well, it prevents this problem called co-adaptation, which is a fancy way of saying a few neurons get too comfortable and start relying way too heavily on each other. And the result is a way more robust network. With dropout, no single neuron can get lazy. It can't just rely on its neighbors to do the work, because its neighbors might be gone on the next training step. Each neuron is forced to pull its own weight and become a much more independent, capable feature detector. It's kind of like you're training a whole army of slightly different, smaller networks all at once, which makes your final model incredibly tough. All right, time for the data boot camp. Look, if our model isn't ready for the real world, we've got to make its training ground a whole lot tougher. You know, one of the best ways to fight overfitting is just to throw more data at it. But what if you can't get more data? Simple. You make it. By creating all these slightly tweaked versions of our existing data, we can teach the model this crucial concept called invariance. Basically, the idea that a cat is still a cat, even if you're looking at it upside down. It's super powerful. For example, we can start with just one picture of a dog. Then, we can teach our model that it's still a dog if we flip the image or rotate it a little, or maybe change the lighting or zoom right in on its face. To the AI, every single one of these is a brand new piece of information, a new learning opportunity. We've just massively expanded our data set pretty much for free. And we can get even more creative with techniques like cutout. I love this one. We literally just erase a random square out of the image. Why would we do that? Well, imagine a model is learning to identify birds. It might get lazy and just learn to spot a beak. But with cutout, what happens if we erase the beak? The model is forced to learn from everything else: the wings, the feathers, the background. It makes it so much smarter. And then there's this one called mix-up, which is just a wild idea. We literally blend two images together. So we take, say, 70% of a cat image and 30% of a dog image and mush them together. But we don't just mix the pixels, we mix the labels too. So we train the model on this weird new ghost image and tell it, hey, just so you know, this is 70% cat and 30% dog. This forces the model to be way less overconfident and to make much smoother, more nuanced decisions. Okay, our last big strategy is all about timing. It's the final whistle. It's about knowing exactly when it's time to stop training. This technique is called early stopping, and it's incredibly powerful but also really intuitive. Here's how it works. While we're training our model, we give it a little surprise quiz after every training session. And this quiz is on data it has never seen before. We call this our validation set. At first, its scores on both its training work and the surprise quiz will get better and better. But there will be a moment, the exact moment it starts to overfit, where its training score keeps going up, but its quiz score starts to get worse. And that's our signal. That's when we stop everything. So here's exactly what that looks like in practice. Look at the training loss. That's the model's performance on the data it's memorizing. It just keeps getting better and better, right? Down, down, down. But the validation loss, our little quiz, tells the real story. It gets better, down to 0.20, then it hits a sweet spot, a low of 0.15 at epoch 60, and then it starts getting worse again. That's it. That's our alarm bell. The model from epoch 60 is the one we keep. It's the one we saved right at its absolute peak performance. And finally, let's talk about your complete AI toolbox. Because knowing the tools is one thing, but knowing how to put them all together is where the magic happens. And this right here is probably the most important takeaway of all. In the real world, you almost never use just one of these techniques. The absolute best, most robust models are built by layering these strategies together, creating multiple lines of defense against that villain, overfitting. So a really powerful, state-of-the-art recipe might look something like this. You'd start with L2 regularization to keep all your weights small and balanced. Then you'd add dropout on top to make sure your neurons are independent and robust. Then you throw a ton of data augmentation at it to get it ready for real-world chaos. And you wrap the entire process with early stopping, which acts as your ultimate safety net. See? Each tool is tackling the problem from a slightly different angle. At the end of the day, regularization is what elevates an AI from being just a fragile memorizing machine into a truly robust problem solver. It's the bridge between an AI that works in a lab and an AI that can actually work out here in the real world. So you've got the toolbox now. The only question left is, what are you going to build with it?